Okay. This is the most likely yield line pattern for a square slab, subject to either a uniformly distributed load or even a concentrated load at the middle. It's going to break like that. This has been experimentally proved. This is a test done on a square slab. Here there are beams provided, and there's a pillar support here. And this is the bottom of the slab, it's uniformly loaded. There are beams here which are relatively stiff, spanned by 12. And yielding has taken. Yielding starts here and it propagates and goes there. There are other modes of failure. For example, if you have no beams, no wall, only column here, column here, column here, then the yield line will form like that. Okay? So these are the two common modes, but this is the most common, classic mode. Now, you have to know how to calculate the collapse load. So we are doing a limit analysis, but we are not looking at sequential formation of hinges. We are looking at the final stage. Yield line has formed, and this has become a pyramid, and this point has gone down. There are two simple ways of analyzing this. One is called the principle of virtual work or virtual displacement. We look at that. So let's take any one triangle. And all triangles are actually identical because it's symmetrical. If you take any one triangle and we assume that you give an imaginary deflection, a virtual displacement delta at the center O, then this will go down and the yield lines will undergo some rotation. The rotation is given by, so there's one triangle going down, there's another triangle going down, it will be given by, how to find out how much it goes down? What's the change in angle? Delta? This yield line, it's separating two slab parts, right? So to get the change in angle, if you want to do it the inclined way, you have to take any line which is perpendicular to this line, right? For example, this line itself is perpendicular to that line. So what's the total change in angle? Delta divided by half this length into 2, because you have on both sides. But that's a difficult way to do the calculations. The simplest way is, as we saw earlier, whenever you have an yield line inclined to the two axes and the reinforcement is perpendicular to two axes, you can resolve it in each direction. But here you don't even have to do that, because you realize that the double arrows pointing downward. Do you know why? We're seeing a plan view of the slab. Why is the double arrow pointing downward and not upward? Because it's a sagging moment. Sagging moment. Can you understand? So it's kind of anti-clockwise, which if you take a screwdriver and turn anti-clockwise, the screwdriver will come out. That's the double arrow. Is it clear? You should understand the vectorial notation of this arrow. Now this you can resolve, and you'll find that this component adds up, and this the horizontal component cancels out, right? So the net moment, if you project, is very conveniently obtained in this direction, right? And if m is the moment capacity per unit length, the total moment is m into L. L is the projected length. Clear? Now, so the internal work done, how will you calculate the internal work now? Internal virtual work. See, work is either force into distance or moment into rotation. So to get the rotation, if you understand the previous proof, you have to see basically how much this triangle has rotated with respect to this axis, right, vertical axis. So let that angle be theta. That angle will be nothing but the angle of rotation about this axis, right? So if this O goes down by delta, what's that angle theta? Perpendicular to this projected length. It will be delta divided by L by 2, or into 4, because you have 4 such triangles. Each triangle will give you, the E line in each triangle will give you this much, and theta is delta divided by L by 2. Got it? So this works out to 8n delta. Now, don't get confused about the units. The unit of work is in joules, Newton meter or Newton millimeter. Now, this is your millimeter part. This moment is kilonewton meter per meter. So the meter cancels off. So that's how net quantity is still matching. So this is your external virtual work. And those who come late better learn on their own. Sure question in the NSEM exam. Okay, not exactly this, but one of the earlier ones. Now let's say you put a concentrated load at O. What's the external work done? PU into delta, very easy. So all you have to do is to equate these two quantities, external virtual work to internal virtual work. Equate this to this, and you've got a solution. PU equal to 8m. Again, don't get worried about the units. M is kilonewton meter per meter, which is kilonewton. That's why the units are matching. It's 8m. Got it? That means if you give me a slab, if you give me this slab, and this is experimentally proven, yeah, and you put isotropic reinforcement in it, and you find out the moment capacity. When you find out the moment capacity in a lab test, you should remove all the partial safety factors. And you should also take care of one more factor. I'm telling you in practice. What is that factor? Remember the stress strain curve, we limit to 0.67 FCK. Why do we do that? Two reasons. One is sustained loading and the other is size effect. Size meaning the real slab is much bigger than the cylinder. Sustained loading means in the cylinder you finish the test in 2-3 minutes, but the actual loading takes years, right? So instead of 0.67, or if you take 0.85 F-C, 0.85 cylinder strength, in practice you should take something more. How much more is debatable. People sometimes take 0.9. Sometimes people take 0.95. At least you can take 10% more. So 0.67 FCK, you're removing the partial safety factor of 1.5. 0.67, you can take 0.7, 0.75. 0.75 usually gives very good results in the lab. Is it clear? When you do a test, you should remove all the additional factors that have come into the code equation. And you should use, for the steel, you must test the steel and find its actual yield strength, and not the Fe500, because you may get some higher value. Now you get a higher value. This test was done using mild steel way back in 1962. 69, okay, in 69. And they gave the values of the yield strength. So this is done in UK. The yield strength was 390 megapascals, because it's not 250. So you have to get the correct value. Okay. So you do that, and actually you will get a higher value of PU in practice for one reason. The reason is you have membrane action, which is a little difficult to calculate, which is also a function of how much deflection it goes down. In classic E-line theory, it doesn't come, but tests have shown that this value can even be double. This is a minimum value. Okay, right. Now, if you have a UDL, then tell me what's the total virtual work. See, this was easy, PU into delta. This quantity is the same for all, because that's coming from the cross E lines. But the loading now is WU, small WU, right? Kilonewton per square meter. If it's a UDL, What is the expression for the external virtual load? This point in the middle goes down by delta. It's the height of your pyramid. What's external virtual work? Volume of the pyramid, that's one way to do it, but in an easy way. What you should do is you should take one slab part and see how much the CG has gone down. Right? So if you take the triangle, the load on this is WU into L squared by 4. How much, if you take the resultant of the load and put it in the centroid, how much will that point go down if this goes down by delta? Huh? Delta by 3 or 2 delta by 3? Delta by 3. The reason is this goes down by delta. So the CG is here. This distance is 1:2, right? So if this goes down by delta, it will be delta by 3. So you're right. Goes down by delta by 3 and then you multiply by 4 because there are 4 such triangles. Easy way to do it. But you can also do a volume integral and it's a volume of the pyramid. Do we have it? That also works out the same. So now you got a formula. Equate the same internal work and you get 24 m by L squared. Remember? So elastic theory, if you study it carefully, suggests that the maximum moment m is W L squared by 20.88. But E-line analysis says it's W is equal to, m is equal to WL squared by 24. So any square slab, if you have to quickly do a design for WL squared by 24. Remember, if it's one way, it's WL squared by 8. So you would expect two way it to be half, 16, but it's much more. It's 1/3. It's a little surprising, but that's what it comes. And actually when you test it, it'll be even more because of the tensile membrane action. Got it? Understood? Very easy. So square slab is child's play. Now let's say that this is fixed or continuous. So you have some negative E lines. Tell me what change will you do now? This we've already learned. The positive E line has this much. Negative E line, what should you do? You should put one more arrow, right? What's the direction of the arrow? Let's say the moment capacity is m dash per unit length. The code says you must bend up 50% of the bars or put 50% extra compared to your bottom steel, right? So usually m dash is 0.5 m. So will it take more load? Yes, it will, because you got that steel also is going to yield, right? So in this analysis, I have to put one more arrow. Will it be pointing down or up? In other words, will it add to the internal work or subtract? Huh? It will add. By the way, all internal work is positive. It will add. And you should know that if you have a beam, the sagging moment will be anti-clockwise and the hogging moment will be clockwise, but both will be in the same direction. Am I right? So you should intelligently mark it like this. Anti-clockwise, hogging, but they actually are pointing vectorially in the same direction. Are you getting it? No? You have a hinge here, you have a hinge here, you have load here. This is sagging moment. This is hogging moment. Both are in the same direction. This I am showing with a double arrow on the left side. Got it? This is M dash L. Of course, there will be shear also. I am not showing the shear. Got it? You must get the arrows correctly. Then your answer is very simple. Your internal work is simply M plus M dash, finished, because you have 4 such E lines. And so you can get the answer very easily. So wherever you had M, you just add M dash, finished. So you get 50% more. The strength goes up 50% more. The load capacity goes up 50% more because that steel is also yielding. There's another method. which you can use, but you have to use it carefully. It's called the equilibrium of parts method. It's an alternative. In this method, the free bodies of the various fractured slab segments are considered. So it's of parts. You're not doing equilibrium at every point. With appropriate bending moments, twisting moments, and shear forces applied at the boundaries wherever applicable, in addition to the applied external loads. So, for example, in a beam or a one-way slab, we've done this before. You take this part, L by 3. In limit analysis, we've done that, and then you can. You know exactly where the hinge is going to form, and you just did equilibrium. You didn't look at the deflected shape. You understand it? Here you only look at equilibrium. Whereas here you are taking work, that means you're multiplying the load by the deformation. Here there's no deformation. Clear? Okay. In two-way slab systems, however, the shear forces along the slab's segment boundaries are generally statically indeterminate. You know that. In one-way slab, if the total load is W, if it's symmetric, W by 2, W by 2. Or if the E line is coming at 1/3, 2/3 of the load will go there, 1/3 will go there. But in two-way, it's the shear forces, you know, the corners will lift up, sometimes you'll have uplift there, so it's not uniform. It's a non-uniform shear force, which you'll correctly get if you do elastic analysis, you know. If you have a lot of nodes there at the boundaries, the reaction at the nodes, you can draw a distribution and you know, it's more in the middle and less near the supports. Okay. For convenience, they may be resolved to statically equivalent concentrated forces called nodal forces at the two ends of each E line on the two slab segment free bodies separated by the E line. In the special case where the E line meets the free edge at right angles, 90 degrees, the nodal force is 0. So if you have nodal forces, it's complicated. So if you have situations where the nodal forces are 0, it's very easy to do. So in the exam, at the most I'll give you where the nodal forces are 0. Also, that when you have a junction of three E lines by the same reinforcement mesh, the nodal forces are all 0 at the junction. So no nodal forces here, no shear forces there. Then it's very easy to do. If the E lines are either all positive or negative under this condition. So now let's look at this. We're now going to do equilibrium alone. So we say the total load PU is being shared by the four slab parts. By this slab part is taking PU by 4, this is taking PU by 4, this PU by 4, this PU by 4. Is it a fair thing to do? It's symmetric. Then you look only at equilibrium, which means we already know that the moment here is ml. We know the moment here is 0. And if you take moments about this boundary, the load WU L squared by 4 is having a moment of 1/3 into L by 2. Agree? About this edge. And that is balanced by M into L. Right? This gives you the same answer. You understand? And if you had M dash also, no problem, you get M plus M dash. So it's another clever way of doing the same problem. Now let's take more difficult cases. Let's take a rectangular slab. The rectangular slab, let's take a simpler case of isotropically reinforced. Now, elastic theory says that's a stupid thing to do. Why? Because in the short span, you'll always get more moments than in the long span. But limit state analysis, E-line analysis, you can do anything you want. You can put any amount of steel you want, and that has a solution. So it could be isotropic. So let's take a look at what happens if it's isotropic, then we'll do orthotropic. So here we are saying that you put the same steel in this direction and this direction, for whatever reason. Maybe it's minimum steel, so you need the same on this direction. So typically, there's an aspect ratio for the slab. A is the short span, B is the long span. And we don't know, this 45-degree assumption is convenient for finding the load in the beam. The code gives you that. But the E line may not form at 45. So let's say this distance is x, but it's symmetric, so there's also x. And so what is left behind is b minus 2x. Got it? But we know that this is going to form bang in the middle because of symmetry, and that is a by 2. So first you must draw the yield line pattern correctly. Now this has a solution. Let's say UDL is W. How do we find the solution? Well, if you take external virtual work, what we do, I want you to understand the method. It's not difficult. So whatever little I'm showing you, you must know it inside out. We'll do both ways. Principle of virtual work, equilibrium of slab parchment. Let's do principle of virtual work. Principle of virtual work, this is going to fold up like a pyramid. Got it? Goes down. All four are similar, identical, in addition to being straight. Got it? Okay. Then there's a fifth yield line. What is the fifth yield line? EF. Very good. Now we are going to give a virtual displacement. How will you give delta? The whole thing will deform. Where will the deflection be maximum? In the mechanism. Huh? You tell me in terms of the lines. EF will go down. It's like the ridge of the pyramid, inverted pyramid, right? Now, I want to find out if EF goes down by delta, then how will I do, what's the best way to do my external work? I want you all to try this. I want to write an expression for my external virtual work. All of you try it. And if you like it, I can give you a similar example in your exam. Shall we give them a gift to wake them up? Huh? Now there's extra energy to solve the problem because you get some money out of it. What's the external work? Quickly, I want a formula in 2 minutes. What did we learn from the square slab? That in triangle, if the UDL, the uniformly distributed load is W, the work done is the area of the triangle into W into some fraction of delta depending on how much the CG goes down. Right? So, if you had to divide this into parts, how many parts would you divide it? Will you take this trapezium? Will you take this trapezium? Trapezium is not good. Why? Why is trapezium not good? Finding the centroid of a trapezium unless you have mugged up the formulas is not easy. Which is easiest? Rectangle, right? So we can take this rectangle and we know that the area is b minus 2x into a by 2, and we know that into W is a total load, and we know that the CG will go down by delta by 2. Got it? See, you are not stupid, you are intelligent, though you have to be spoon fed. Half the spoon is in your mouth, the rest half you swallow. Okay, so this is fine. What about the triangles? How many triangles are left? 1, 2, 3, 4, 5, 6, 7, 8. Beautiful. 8 triangles are there, and the area is easy to find out. How much does the CG goes down for all 8? If F and E go down by delta. How much? Any triangle, the CG will be at 1/3 location from the supporting edge, right? So if the corner is going down by delta, how much will the CG goes down by? So easy it is. You do it just like that, the answer is very simple. Area of one triangle into delta by 3, and area of one rectangle into delta by 2, and you can put the appropriate numbers, you get this answer. Please do it yourself. I've told you the method. Very easy. So you got an expression for external virtual work. Note that the displaced slab is in the form of a hipped roof, and the same result can be obtained as a product of W and the volume under the roof because you're integrating. Got it? Good. So let's say we got this. We'll figure it out later. The internal virtual work is also easy. Why? The work done by EF is very easy. How much is the work done by EF? So the total internal virtual work is the work done by EF plus 4 times the work done by AE. Got it? What is the work done by EF? First you take the length of the yield line. What's the length of the yield line? B minus 2x into M. Right? B minus 2x into M. And what's the total rotation? Both sides. Delta divided by A by 2 into 2. Total change in line 2. Got it? So that work you know. What about this? This you can resolve into 2 directions. You can resolve into the component in this direction, which is A by 2, and a component in this direction, which is X. If you take the component in this direction, A by 2, what is the rotation about this edge? It is delta divided by X. And if you take the component in this direction, X, what's the rotation? Delta divided by A by 2. Finito, nothing more to do. That's all you do. You go home and read all this. I told you what to do. One step you get the answer. Then if you equate it, you get an interesting expression. W and delta will cancel because it's on both sides and it's virtual. Now is the interesting part. Actually, how many such patterns can you draw? You can draw infinite pattern for different values of x. X by L, right? So how will you find out which is the correct x? That which gives you the minimum load capacity for a given M. So it's very interesting. After you write this expression, if you pull out M by WU and you get it in a form like this, then you have to take the derivative of this and make it 0. Either M by W or W by M, it doesn't matter. So this is a function of x, this is a function of x, this is a constant. So you know how to take the derivative of this. So the derivative can be written like this. So the numerator should be 0. See how clever this is. So you got u, you got v, v dash u minus u dash v equal to 0. You solve, you get a quadratic equation x, beautiful expression for x. Got it? By the way, this problem was cracked 50 years ago. Johansson did it. Hats off to him. Then he said, now is the tricky part. If you take this equation and you put it back here, it's going to be messy. So people said there's a clever thing you can do now. You can combine principle of virtual work method with equilibrium of slab parts method and you can get a quick answer. How do you do that? Well, substituting this value, okay, however the result is more easily obtained by invoking the equilibrium of slab parts method and considering the equilibrium of a triangle segment ABE alone. ABE alone. Take this triangle. Remember, it's not different from this triangle. So you know the trick. Take that triangle and then you can write W into x by 2 into x by 3 equal to mx. Same logic. So W equal to 6m by x squared. X, you've already got a beautiful formula. You get a formula for W or you can get a formula for m. This formula you will use when you're doing analysis for a given rectangular slab with given moment capacity m. This formula you will use for design when you want to find out how much m to put in the slab for it to work. Got it? And you can check that when you make this into square, that means when A by B is equal to L, this simplifies to W, the same formula for a square slab by 24. Got it? Interesting. The next thing to do is what happens if it is orthotropic. It's stupid to do this isotropic, you're wasting your money because in the longitudinal direction you should not be putting so much steel. So then you will bring in a new factor called mu. Okay, so in the main span direction, that means these three lines show reinforcement in the short span. Moment capacity then. in the long span direction, we'll give something less than this. So we give mu times m. Mu is typically called the orthotropy coefficient. Mu is usually less than 1, but some crazy people can even put more than 1. You will still get a correct answer by E-line analysis. Got it? So that's your mu. You can redo all the calculations. I'm not going to spend time. I won't ask you this question in your ensign exam, this for your reference. And here by equilibrium of slab parts method, you can solve this, you get another equation. But now the only difference between that equation and this equation, you've got a square root of mu term coming in between. If you put mu equal to 1, you will get back the old equation. Got it? So you know how to do square slab, you know how to do rectangular slab. Got it? And this you will need in practice. And the chord coefficients are actually taken from here. Now let's do one or two, we have time. Tricky questions. Let's take the balcony slab. The balcony slab, let's say it's simply supported on 3 sides. I'm not giving a support here. Right? Now there are two ways E-lines can form. Either they can form like this and not meet, or they can form like this and meet. So a good designer will get, for a given ratio of A by B. Sometimes, in some cases this will govern, in some cases this will govern. Right? So I need a solution, and let's say it's isotropy, M equals both directions. I want to find out how much is the moment capacity. I want to find out how much is the ultimate load capacity, collapse load. So this triangle you are very comfortable with now. We've done many triangles. This is a triangle which you can divide into 2 parts. So actually you can do this again. Here you have to be careful. You can't use equilibrium of slab parts method directly because you've got some nodal forces, because this E-line is not orthogonal to this line. Okay, so you have to be careful. But virtual work method will always work. Please go through this example also and just see the results. The E-line pattern. So we've got both the solutions. This is one solution, this is another solution. Just read it. I'm not going to ask you. If at all I'll ask you a very simple E-line problem. What do you think is a simple E-line problem? I'm going to ask you 2 E-line questions. One E-line question is, I'll give you a shape with some supports. You have to guess the most likely E-line pattern following the guidelines that you've been taught. It's going to happen this way. That's how. If you do that, how many marks? 1 mark, 2 mark?
2 marks. 2 marks.
2 marks for guessing correctly. You guess it wrong, 0 marks. Okay? If you draw one which looks decent, but when you extend it, it doesn't meet the extended lines, you get 1 mark. So 0 mark, 1 mark, 2 marks. 3 options you have. Okay? Right. Second one, you actually have to give me the collapse moment. Give me the collapse load. Or for a factored load, tell me how much steel to put. So what do you want? Do you want a square? You want a rectangle? You want a triangle? Triangle is easy, no? Huh? One-way slab. No. Considering a square panel, you'll find that this is this value, this is this value is lower than this value, so this is more likely to happen. Got it? Circle! We'll solve it for you, but we won't ask you in the exam because you said no. Okay? We'll solve it. So, this is a circle, and you can have 2 cases. One is it is simply supported, the other is it is fixed. Simply supported and fixed, right? And you can have 2 load cases. One is UDL, the other is concentrated load. Okay? Why don't you go through this? It's a very nice proof. The answer is WU is 6m by r square, and if you have a negative E line, it is 6m plus m dash by r. But sorry, we won't ask you in the answer because you didn't want it. Actually, it's a gift if you had got it. But you are mature people, you don't deserve such easy questions, so we'll skip this, but I want you to read it. So you can prove concentrated load. Okay, so E-line analysis is covered. I've leaked out the question for you. The moment distribution question. We were trying to set up, I gave you a clue, no? but I'm still doubtful whether you can do all that moment distribution. Can you do it? I've got to ask you a question. So I'm going to ask you something simpler, not two-span continuous beam, but it will be a beam. What it is, I won't tell you. Could be fixed beam, could be propped cantilever. It's easier than two-span continuous. You don't have to do much moment distribution now. Is it clear? But you have to learn all the rules. How much of moment distribution is allowed? What is the redistributed diagram going to be like? So definitely one good question you will get on moment redistribution. And two small questions on E-line theory. Got it? Okay, I just want to cover something.
Why do we raise it for 3D into L by 6?
Sorry?
The entire bending moment diagram or redistribution. Why do we, like at support, why do we raise it by 3D into L by 6?
You're speaking too fast. You're from Bengal, no? Even she can't understand. Once I was traveling in a tram in Calcutta. He's from Calcutta, I know that. Tram, you know tram? In Paris you have trams? Yeah. You've seen trams? Electric moves very slowly. So, it's a wonderful vehicle. Why? You can really look outside and enjoy life. And in Calcutta anyway nothing moves. Traffic doesn't move. Thanks to this government you voted in, it moves even less. Nothing moves. So if you sit in the tram, somebody asked, foreigner asked, in front of me it happened, where does this tram go to? So someone like him said, Bibbidi Bug. Where? Bibbidi Bug. Now you understand. So how should you answer? B-B-D Bug. What is the full form? Binoy. Then?
They were all freedom fighters. So
okay, slowly you tell, no? Binoy?
Binoy, Badol,
Badol.
and Dinesh.
See how nice it is. Bengali is a sweet language. But what was the question?
Why is it?
You only ask the question, yeah. Slowly you ask. So
Why is the bending moment increased? Like the bending moment diagram is raised at the support by
bending moment diagram is raised at the support
we
in
consider
a beam.
like load actually.
Load.
I mean
You come to the board and explain.
the span moment is reduced.
Span moment is reduced.
Support moment is increased because of stiffness at the joint is higher. So VB into L by 6 is given.
Oh, you're talking about the beam column.
Beam column joint.
No, that is based on a lot of studies done. You're saying why is it VB by? That's based on a lot of studies. So let's not get into that. Just accept it. That's a fairly conservative way of doing it. But it's not exactly that. It's based on some assumptions. I've explained the assumptions also in the book. Read it. So that same chapter, okay, this is the beginning chapter. Did I show you this earlier? So normally when we study reinforced concrete, we should begin with introduction, unless the students are already mature. So for immature students, we begin with first saying what is the building. So typically a multi-story building will look like this, a structure will look like this. A good engineer will try to see the skeleton in it. How does it work? So this is called the framing plan. So really the frame, it's a frame structure. So you have columns and you have beams. Do we have the tube and all that in this? It's there in the book, the beginning chapters you can read. Now, we for convenience separate out the frames in the two directions for analysis, unless you want to do a 3D analysis, right? The assumption is the interaction between the frames in the longitudinal direction and the transverse direction is not much, especially under gravity loads, unless the beam is highly irregular, in which case it could even twist in plan. So we can take and this is called a plane frame, and this is called a slab, right? You've got primary beams and secondary, these are primary beams. So you treat the slab, the gravity load on the slab to be taken by the beams, and the beams transmitting load to the columns, and the columns going all the way to the foundation, right? This is gravity load. And the same load you transmit to the beams and the columns, and you have this plane frame on which you apply the load. Now the plane frame not only takes vertical loads, it also is the main lateral load resisting system in the structure. So you must have enough frames. And one big question comes, if you have a lateral load acting on this building, how will you distribute the total lateral load to 1, 2, 3, 4, 5 frames? How will you distribute? You got the lateral load. How is it done in practice? Tributary area. You say that the exterior frame, if this is equally spread out, the exterior frame will take half the load compared to the interior frames. Yes? Right? Now, is it a correct assumption? I'm glad we are raising this topic. You have to find lateral loads on the frame, right? But how do you arrive at these lateral loads? So that's where 3D analysis will give you a better understanding, but you can use your common sense. The first thing you have to note is that if this building is going to sway in such a way that the whole building moves together, this moves here. Then, and if let's say the sway is the same for all the frames, what does it tell you? And when will that happen? That happens if you've got a rigid diaphragm. You know what a diaphragm is? What's a diaphragm? How many diaphragms are there in this room? 2. Inside you, is there a diaphragm? What's the spelling of diaphragm? D-I-A? D-H-A? P-H? Oh, it's there. That sometimes people miss the G. P-R-A-G-M. Diaphragm. What is the job of a diaphragm? What's the job of a diaphragm?
Create something for us to breathe in.
In a box girder, you have a diaphragm. What's the job of the diaphragm? It's a cross element which the whole idea is to integrate and make sure it doesn't fall apart, it behaves together, right? Similarly, there's a muscle inside, you know that. It's a diaphragm. When you breathe in, it goes up, and when you breathe out, it goes down, it pushes your abdomen. So that's it's a separator, it's what holds your system together. Similarly, you have a rigid diaphragm here, which is what is connecting all the 5 frames and make sure they displace more or less the same. If you have a stiff diaphragm, then it ensures that the whole thing moves like a rigid body. It could twist, but it will again twist like a rigid body. If you have a flexible diaphragm, it's going to deform such that when the wind is acting, the middle region will move more than the end regions. Let's consider a rigid diaphragm. If all the frames move exactly the same, what does it tell you? It tells you, because lateral stiffness is what decides how much it will move. It tells you that all the frames will take the same load. So this assumption of tributary area, that due to wind load only the middle region will take 2 times, this is a stupid assumption. Stupid? You don't like the word? Many colleagues are stupid because they make this assumption. But I'll tell you a bigger secret. The truth is, the exterior frames take more load than the interior frames. Can you tell me why? Here they are equal because the diaphragm makes them equal. But I'm saying something, even they all move laterally the same and all have the same dimensions and same material properties, the end frames actually end up taking more load. Why? Potential quiz question. Why? They are stiffer. Why are they stiffer? Why is this frame stiffer than this frame? Weak students, mature, immature, you decide. You tell me. Why is this frame here, the end frame, the building ends here, more stiff than the interior frame, even though the beam size, column size is exactly the same? Why? Imagine you're the frame and someone's trying to push you. Because there's an infill masonry wall here with right in front of your eyes which you are not willing to look at. This frame has no masonry wall. So when you push the frame, you have to also push the wall with it, and the wall is not easy to push. Wall is little rigid. Wall will resist it, and the stiffness of the frame can even be double. There are lots of studies done on how much the stiffness is. It's not less. And look at the tragedy. BBD Bug says that.
I was taking the question in a different sense.
No, I'm asking you what sense.
I have a different question. For the internal
No,
frame.
wait. First, I've seen this picture, I'm trying to tell something which many engineers ignore. I'm trying to say that you're right. In practice, people say, look, wind is acting on this wall, and this tributary area is 2 times this tributary area. So 2 times the load will come here. That's not how you should do it. You should get the total load on the building and distribute it to the frames in proportion to their lateral stiffnesses. And the end frame will have a larger stiffness. What's your question?
In the portal frame method, we assume that the columns are exactly taking half of the.
That's a different thing. Wait. You have advanced from the building to the frame. I'm not yet gone to the frame. In the school, in your BTech level, someone drew one frame, drew this and gave you these numbers. Where do you get those numbers from? First you have to get the number, first you get the load, first you have to have carrot before you can make carrot halwa. Yes or no? Who gives you these forces? You calculate how. So we are going step by step, yeah? Okay, now we'll come to your question. Yeah.
Okay, I'll ask you.
No, now only, yeah? This is the last chance.
So for the
We don't have any time left. By the way, Indu is going to take tomorrow's class on, am I right? On Stratton time method. And Sharif is going to take he has the last word, Donald Trump. We are only vice president, he is the president. He is going to take the last class on detailing, and of course I'll be also there. Okay, so we don't have time. Are you willing to sit a little late today? I want to show you that case study. That's why we've got some visitors here, they want to listen to that. Yeah. Tell me, what's your question?
for the portal frame method, we are assuming.
Portal frame method. Slowly, yaar. Portal frame method. Like a bullet, yeah. For the portal frame method,
For the portal frame method, we are assuming that lateral load
we are assuming that the lateral load,
is distributed equally to each individual portal. So
each
that
individual portal.
each way of the portal.
Okay.
The exterior columns are taking half of the load, whereas the interior columns are taking double load.
Right.
So that is, I think it is true only
It's true.
if the beam members are axially reaching. So the shear will be.
So this is a convenient method, otherwise it becomes statically indeterminate. It's strictly not true. You have to have some way of, you know what's the right thing you should say? You have a story shear. What is story shear? You assume points of contraflexion at mid height of all the columns. You take a knife and cut the frame at that level, starting from the top. You have some lateral shear. At every story, you have a sigma column shear forces which must be equal to the load you're applying. Now you want to pass on that shear to the different columns in some proportion. Some people say it's in proportion to the bay width. Different theories are there. Some people say let's make it simple. Let's say the interior column takes 2 times the shear as the exterior column. What's your question?
So the relative stiffness is
No,
also
what's the question? No, there's no stiffness here.
That is.
There are 3 approximate methods. One is called portal method. Second is called the cantilever method, where you don't make these assumptions. There's a third method called the factor method. Factor method is the more accurate, okay, because you're bringing in relative stiffnesses which you didn't bring in the first 2 methods. So if you want to bring it simple, do the factor. Question clear? Okay. In my book in structural analysis, I've discussed these 2 methods exhaustively, why we are making these assumptions. But it's an assumption. You said in your term project, I hope you're submitting your term project, you did it by STAD,
By both actually.
and you say that you're getting widely different results?
Point of contraflexion is not coming.
That won't come. I'm asking you, is your bending moment widely different?
Magnitudes are small, but they're different. The magnitudes themselves are small, but
That's okay.
It's around 50%.
That's okay. That's okay. Let's say the correct answer is 0 and you got 0.1. I'm asking you, what's the percentage error you're making? Correct answer is 0. He got 0.1. What's the percentage error you're making? Infinite. 1000%. Must be wrong. It's okay, yaar. 0.1 is as good as 0. So don't give me this percentage bullshit. It doesn't make any sense. Both are kutty things, yaar. And it doesn't govern the design. That's why I gave you a 2-story building. You understand? Let's say you go to somebody's house and you're a structural engineer. You have a crack in your wall. One small 0.1 mm crack on the wall. Said, oh, what to do? Said, you better do something. But you fail to observe that there's a 5 mm crack in the beam, and the beam is a structural element, wall is a non-structural element. You're making a big fuss about something that is not important. But the beam, the steel has yielded. So you must know what is important and what is not important. You must know what is structural and what is non-structural. So you don't have to worry too much. So you have to be careful when you talk of percentages, error and all that. What's the significance of it? What's the significance in terms of serviceability? What's the significance in terms of strength? That comes from practice, from that. Okay. To the end, I'm going to show you. So the diaphragm serves a useful purpose, and then you know how to distribute this. I showed you this slide earlier. You've got frames in the X direction, frames the other direction. This is what I want, and you can do substitute frames. This is all there from the book. This is what I wanted to show you. You can use Müller-Brislow's principle to find out where to put your live loads, right? You know the principle. So let's say I want to find the influence line for bending moment at G. I must have a unit displacement here, unit rotation here, which is possible only if I move it up or down. So I move it up, and the relative change in angle, if it's 1 radian, whatever shape I get, that's the shape of the influence line diagram. I've already given you the meaning of the influence line diagram. So if I say if this is positive, then if I put a unit load here, this is going to come down. The moment is going to come down. So wherever it's positive, I should put the load. Wherever it's negative, I should not put the load to get the worst effect. So learning from this, my dead load is constant everywhere. I put my live load here and here to get the peak value here. But it's quite possible that I might hit a minimum. So now I do the opposite. I put live load here, and live load here, no live load here, no live load here. I possibly get a negative moment here, which I should worry about if the span is small. If I want for a support, say at C, then I give a hinge there, and my difference in rotation should be unity here. Then you'll find 2 adjacent spans in every alternate span. This is what I wanted to explain to you last time. Similarly, if you want to do it as part of a frame, this was a beam, you can do the same thing, and you can keep drawing these diagrams to understand where. It's a very powerful method of doing it, and this is usually done in bridges. Now I'm going to tell you about a case study of a building. I used to be at this place, Calicut. When was this? This project we got, I joined REC Calicut after working in Delhi for 5 years in 1985. This building we did in 1986. And I had a major role in this because I was supposed to have a lot of experience having worked in Delhi. A very interesting project. This is shaped like a ship. And it's in Cochin, which is near a harbor where you have lots of ships. This architect is a very, very famous architect, Adam Salim Associates, with whom we've done many projects. And he came to us because he says this is complicated. This is a 5-story building. The entire roof is supported on 4 columns. And it's all made of reinforced concrete, except this is concrete, but this roof is steel. Now, how did we design this? I just want to show you it's a very challenging project. recently they called me again. It was after 1986. 2 years back, they wanted to do an extension inside the badminton court. They wanted to put some more structure, so we helped them. This came in the first edition of this textbook. This was released in 1998. Okay, so there are many frames inside here which are like this, and we'll discuss different elements in this structure. How it's good to have a big picture idea, then go to it element by element and study how it behaves. This is where the typical gallery ends. So the seating in the gallery starts there, goes all the way there, goes all the way there, and then stops here. And this is your ground, the indoor stadium where you have many games. This was supposed to be for the national games at Cochin during that time. So the construction was done at very fast speed, so the design had to be done very quickly. I remember we produced 56 drawings on tracing sheet. Those days there was no AutoCAD, there was no computer. It was done manually. Okay? But I had a colleague who had just come back from Dubai who had a 4-line display Casio programmable calculator. Programmable calculator. I wish you had brought that file here. Okay? You can just pass it around just to see. I'm just preserving this. It's all done manually. So for memory's sake, I kept some of these. We just pass it. So on that, I did matrix analysis. No FEM. So I wrote the program because I was also teaching it. Wrote the program and did the frame analysis. Also did manually, did a cross check. So I just thought it's nice for you to have a little experience, a vicarious experience. You know what the word of vicarious is? Somebody else does it, but you feel like you have also done it. In this case, we are all bonded together. You are my students, so you should get the feeling. And we involved some students also in it, and they really loved it. It was done very fast. In 3 months, we did the whole thing. Okay, so we were also involved at the construction time, and I want to tell you many problems if you have time. At construction, we were really concerned because they were going with breakneck speed. There are these cantilevers, for example, this cantilever is here, and they were not ready for putting the shuttering for this, and they went ahead and cast the column. So we said this is risky. Why is it risky? You know, typically they leave dowels here. This has to be cast integrally. Do you know why? Because the cantilever has a back span. And if you don't do it, you don't have proper shear transfer. So unless you give a key here deliberately. So we have to intervene at every stage to make sure, and if you have dynamic loads on this, it can break off. So you have to be, every stage you have to be careful of how it's done. The stand sticks out like this at the back, this back side, even this side sticks out. So I'm going to show you different pages of this, just sample sheets. Sharif selected some pages, so we look at that. So basically the calculations were, and this was not proof checked. Those days there was, you said, you guys know the best, you do it yourself. There was no time to proof check. So whatever I did here is all in good faith and done, and hopefully there are no mistakes. But you have to be answerable. So the papers are still there. So plans and framing elevations, design of precast steps, floor and roof slabs and secondary beams, analysis of main frames, design of columns, design of main frame beams, staircases and middle map. This was way back, 1986, 87. Today nobody does this. Today if the client wants a report, the designer is more than happy to do it because he doesn't have to do anything. He has to only press a button, click. And then you get STAD output which comes in 325 pages, and nobody can understand anything from that output because it's all junk and no explanation, nothing. But the client is happy because he's got a record of something printed on paper which is going to fade away in 10 years. We've got so many calculations there, we don't know what to do with it. We are burning all the old files, so there's no place to keep anything. But hand calculations are good because they're easy to check and quick. So I would suggest all of you do your projects, keep some calculation which you can look back into and improve on. Here's a sample of that. The last one was very tricky. We had a helical ram with increasing diameter and nobody knew how to design it. So I gave an MTech project, and the student did a fantastic job, and we found a correct solution. That was the first, and he did by Fortran programming, no software. And in good faith we did it, we did some crude calculation. There is torsion in this, and worked. So the plans are typically like this in one quadrant. These are all hand drawn with scale, with pencil. These are the old ways. And the first thing is to do grids because it's a combined job with the architect and structural engineer. You say, I want the grids. He's made a model. He said, I want this, you do what you want. So he said, we'll give you this. But he said, I don't know how to draw these shapes because these are all inclined, you understand? And you have to be good in engineering drawing to put 3D into 2D. But we had very good people there. We had one Professor Ahmed who was very strong in the drawing part. So he guided the architectural draftsman to draw this, and then there's a perfect match between architecture and structure. Today, of course, your computer can do everything. So we have all these different plans at different levels. It's a 5-story building. So, and typical structural elevation. So you have to be very clear what's inside the building. What's the structure inside, what's the loads you can expect, and then you have to start your analysis. So there are many elevations. Okay. So first you say, before you've got some rough proportioning, but you've got your material to start doing the design. First you get rid of the things which are statically determined more or less, and you don't need to do frame analysis. So the slabs you can do, the steps you can do. So just to show you, the step is interesting. We said we'll do precast those days. But then it's L-shaped step, and L-shaped means it can, and we said we will treat the whole thing as one element. But this is a classic case of unsymmetrical bending. So you have to find out the VV axis. So all that was done. You can get the bending moment diagram in both cases, work out your calculations. There are hand calculations. And then you do the detailing and the reinforcement. And these were immediately cast. While you're doing the other calculations, we gave the drawings for casting the step. We actually cross-checked with each other. They're all faculty, so we got this mutual support. So lots of studies were done. Then another thing, we have to also tell them where to put the hook to lift the step, because in transporting it can get damaged. So we have to plan the hook location. So construction stage activity also, so you can work out the bending moment. We want to make these two more or less equal, and then design it so that make sure the reinforcement is adequate. Then we did all the secondary beams. You see all the calculations. This is how typically it is done. This training I got in Delhi, where we had to do it ourselves, all the calculations, no computer. And you have to show the loading diagram, you have to show the bending moment, you have to do a quick calculation of the loads, find the reactions, find out where your moment is maximum. There's a concentrated load here. That's where your shear force is minimum. You understand? Then mu by BD squared. Then either you have your own program, today we have program, or you use SP16, find out the percentage steel, and then you detail it, that's it. And in Delhi, I remember the draftsmen were hungry. We used to hire draftsmen who were very skilled, who used to work for MES. So that's where we learned Punjabi, because they speak Punjabi, and they like to work at night, and they like to drink. So when the boss is not there at night, you feed them these drawings. They were very good. we learn from them. Really great place to work in, these small companies. So you draft this, the sketch there, give this to them. I mean, you draw it in a piece of paper and give it to the draftsman, he'll draw it for you. So different spans, see the triangular load, the UDL, all these studies were done. Lots of secondary beam. See, you have a continuous beam like this. And then bending over diagram, cross section, you have to check at different locations, and so on and so forth. Whole responsibility of the project is on your head. You can share the load. We only gave the foundation to somebody. The rest of it we did ourselves. Then there's a water tank. See, these all you can do fast. You get the load on the water tank. With experience, you can do that. There's an RC wall, etc. Then you can do the floor slabs, different panels, secondary beams, etc. You have some special detailing correction. See, the red pen is a correction after replanning, redrawing. You have to go back and do it, but you don't need to write fresh. You're a lazy guy, so you take another color and use different colors and do it. So lots of calculations. There's a lot of inclined slabs and walls, so you make some suitable assumption and do it. Typical bending moment diagram, shear force distribution, you should know more or less design from different elements. Some are inclined, some are vertical. Now we'll do something really challenging. How do you analyze the frames? And the frame is like this. And we are playing with these dimensions because the architect was also changing his mind. And the columns were, these main columns were plus shaped columns, 1 meter by 1 meter. 300 plus shape. How do you design a plus shape column? But you know how to do the interaction curve for any column. So I wrote a program which could do it for a plus shape column. Okay, so this is where I did my matrix analysis, member stiffness coefficient, etc. But a lot of load calculations. You can check. Finally, you have to check all the reactions should match up. This part is statically disturbed. This computer is actually a display that you read from a programmable calculator 4-line display. Look at all this. Now, it's interesting to know you don't want too much movement of the frame. So the first intermediate frame analysis, I realized that you got a huge hogging moment in the beam. You can do nothing about it because it's this part is cantilever. It's a huge moment, 4,048 kilometers per meter. But then one problem was this was deflecting too much. And the other problem was that much of this moment is going into the column. The column moment is 2,321 and a lot of it was going to the fixity at the base. It was on piles, 866. So column was becoming very uneconomical. And the back span was taking only 1751. So usually when you have a continuous beam in the back span, most of this moment should go here and less should go there. Right? So what will you do to make that happen? First you have to stiffen this part so that the deflection is less. Secondly, you've got to do some trick so that your column moments are reduced. And the beam, because you're anyway designing this part to take this moment, that same steel should be continued and can take the back span. What's a clever trick you can do? That's why you can have a dialogue with the architect and convince him and then what? Any suggestion? See, this is coming from frame analysis. If you add this moment and this moment, it will be equal to this. But we can't do much about this moment. But we want most of it to go here, and less of it to go here. Right now the column is taking more than the beam. What to do? Huh?
You have to increase the stiffness of the beam.
Stiffness of the beam. How do you do that? So we had to do it in a way which the architect will accept. So we came up with a clever idea and the architect just loved it. Okay, this is the end of the beam. So finally we made this moment 4048. Most of it, 3420 goes to the beam and the rest of it goes to the column and very little goes to the bottom. After you do your frame analysis, it's nice to draw the free body diagrams for all your elements because you're going to do the design. So every element you draw a free body, and if you are a little aesthetically inclined, if you like colors to play with, like crayon, little children play with colors, then you say all the vertical forces I will use blue color, and all the lateral forces I'll use purple color. It's a bending moment, I'll use this color. Then you have to convert the vertical and horizontal to shear and axial by resolving them. Finally, this is what you have to design for. So you have to do it everywhere and take for many combinations and take the worst. But how did we achieve this? I think I have a figure for that. Wait. To do all this, you've got tapered beams. So your software, so you have to find out the modified stiffness. It's not Fourier. You have to do from first principles how to find the tapered stiffness, how to find the carryover factors. A lot of fundamental work you have to do before you can write your program. So you see a lot of basics, structural analysis, and so finally you can validate it, improve it. See, get this unit load. Tapered section, what's the stiffness matrix coefficient for a tapered section? A lot of work was done, but it was good fun. I was a bachelor, what else to do? I used to enjoy doing all this. So lots of calculations like this. See, everywhere you have to draw a free body before you do the design. A beam, you must draw the free body. You know what bending moment you're designing for, what shear force you're designing for. You're crystal clear of the assumptions you're making. Go ahead and do it. So final deflections also you calculate. Now we come to the topic that you learned, design of columns. You've got interesting columns. So first you have to categorize the columns. So I made them all of one size. I said all of them should fall within the traction curve. These are the ultimate loads, these are the ultimate moments, this is the bending moment for different combinations. So I use this. No SP16 will give you the interaction curve for this. So I wrote a program, and for all these columns, you wrote the program and you put column type, make sure all the critical points are within the interaction diagram. I think I've got some diagram also, including this plus shape column. So it's all worked out. Don't we have some interaction diagram? Yes, sir. There you are. Okay, then this tower which goes on top, see that part, actually the roof part, the client was in a hurry, so it was given to the same person who was constructing the roof. It was a steel job, construction steel job. But we told him what to do, and we said we'll just proof check the roof. Roof is interesting. You've got 4 columns. You've got trusses here, you've got trusses here, you've got a huge cantilever. The cantilever is going to be very expensive. The only way to reduce your cost is to prop it with a sling. So we put a cable and picked up the tip of the cantilever, and then we had to analyze the system, so we did it by theorem of least work, because you have the cable stiffness, and that's how you analyze it. And the truss was checked, deflections were checked, it was ordered, and it was fabricated and brought to site and erected. But the column is still got to continue, so this column goes on top. We tapered it so that it goes to a small size on top, and then these are the interaction diagrams. So we found that the top lateral force on the top of the column is so high that the bending moment here is the highest bending moment in the plus shaped column anyway. So here's a classic case where you needed more steel at the top than at the bottom. Very unusual thing because the pull you get from your cable is so high that it comes to this. So that's a pretty high column. So that's how it is done. Everything checked for. Okay, then all these calculations were done. And I want to end with. Then we have the helicoidal staircase, which was a big challenge. Just to show you two slides here. This is what the helicoidal staircase was. You had a plus-shaped column in the middle, and you had a staircase going spirally around it. It has to be aesthetic. With increasing diameter, the architect's very... So he said, normally you have helix with a constant diameter. This is increasing diameter. MTech project, did a fantastic job. Wrote a program in Fortran. You have to satisfy equilibrium, compatibility, and stress strain relationships. And based on that, we did the design for torsion. That's how. Very interesting parts. But in 6 months, in 3 months we finished, but the helical staircase took a little time. Everything was done, and in 1 year the project was over. And today, that is being used not only as an indoor stadium, it's also being used as a hotel. Many of the rooms there are for rent. I stayed there one night, the night they called me. It's a plush place to stay. If you visit, take a look. The GCD Stadium at Kadvandara in Cochin. You go inside and take a look. So that's just to give you an example of how you can do any building. It's nice to do a variety of projects. It's nice to do industrial buildings, nice to do bridges, it's nice to do multi-story buildings. It's nice to do chimneys. My PhD area of specialization was on chimneys. It's nice to do offshore structures, jetties and harbors. And it's nice to do ordinary building. We've done houses. 5 PhDs have worked on this glass fiber reinforced gypsum projects. So if you're a structural engineer, you can do anything. Then I also did work with mechanical engineers, metallurgists and orthopedic surgeons. We have 2 patents on wrist fixators, both in the leg and the bone. So the bone is also a structural element. Then you can collaborate with aerospace engineers, naval architecture people. That's the joy of structural engineering. You have to be open. Even a piece of furniture is a structure. So how to elegantly design these things, how to analyze, how to intuitively guess what's going on, how to make mistakes and how to learn from your mistakes, how to do it slowly. The other thing I want to tell you is that it's a very rewarding profession if you learn it well, and don't expect money in the beginning. But once you are known to be an expert, money will keep pouring in, and it's all white money. And I think real freedom comes in life when you've reached a stage when you're already abundant. Then you choose the jobs that you want to do because they're challenging. You don't waste your time doing it. In IIT here we have, we almost run an office. I don't know if you've seen that. Meher Prasad and I have about 15-20 project staff. And they work here for 3-4 years and they get good jobs. That's one of the reasons we want to be in touch with what's happening in the profession, what mistakes they're making, what challenges there. So we are normally doing a lot of proof checking for both buildings and bridges. We're now doing a very interesting bridge, the cable stayed bridge in Kolkata. I don't know why it's gone quiet. Mike Schleich has sent us some reports recently of the damage done to the first cable stayed bridge. He wants us to help. Second Hooghly bridge. So these are interesting projects, and some of you can. I'll offer you something. If you've not got a job and you want to learn, join us as a project associate. We'll Your experience here will help you get a good job. We also try to choose our PhD problems from the projects, from the problems we encounter in practice. So most of the PhD problems are also identified from doubts we ourselves have. For example, the work Bijli is doing on yield line analysis of the yield line analysis that you've learnt is assuming rigid supports. But what happens if the support is flexible? How do you do it? There's no theory yet, so the entire work is devoted to it. So that's what makes it interesting. I also want to tell you that I've worked both in the field and in academics. And I tell you the real joy is doing both. Real joy is doing both. Then only you get fulfillment. And the big advantage of doing it in an academic institution is you're the boss. So when people say we want it tomorrow, you'll say go home. We don't have time. How much time will it take? We'll say 3 months. And they'll wait. But you have to make sure it's done well, done perfectly. Don't take risks. Know where the shortcomings are. Do a good job. So it's a very exciting profession, but you have to know your fundamentals. You have to know that you don't know. That's a good starting point. Take as many courses as you can. And don't be stuck to structures division alone. Go to applied mechanics. Go to aerospace. Go to wherever you can learn. And lastly, if you really want to succeed as a human being, you have to do more than just engineering. So that's why we offer you courses like self-awareness and integral cognition. Okay, so thank you very much.